Hello, welcome to Math with Patrick. Today we'll be solving the first problem of the 2025 Daily Epsilon Math Calendar from the American Mathematical Society. Thanks to them for creating very fun, rich, and entertaining math problems. And the key to these problems is that the answer is already given to us. It's just this one right here. However, the task is figuring out why the answer is 1. So let's get into it. We have an equilateral triangle here. I know this because all the angles are equal, and so they're all 60 degrees. And I'm also noticing some little tick marks here, and this tells me that these two sides are equal. Now I want to zoom into this little feature right here real quick. So earlier I was saying that I know that this is 60 degrees, and it looks like, well, I'm being told that these two sides are equal. And there's a concept called vertical angles, where if I have two straight lines, the angles opposite each other should be equal. So I know that this one on the inside should be a 60 as well, because it matches the one over here. Currently, this is an isosceles triangle. I know this because two of the sides are equal. And there is a theorem that states that these angles are also equal to each other in an isosceles triangle. Now, if these two are equal and there's a 60 already there, well, I'm pretty sure that they're all 60 then. So this is another teeny tiny equilateral triangle as well. I'm going to take a look at this line and this diagonal. So since we're being told that this is a square in the middle, I know that these two lines are parallel. And if we take a look at this diagonal, or the transversal, there are some things we could tell about angles here too. This tiny guy is right here. We already established that that's 60 degrees. And with this parallel lines and transversal idea, I know that corresponding angles must be equal too. So a lot of mathy terms here just to say that this is 60 degrees, and since that was 60 degrees from earlier, this has to be 60 degrees too. So let's first try solving it as intended, or probably as intended, where these two triangles are the same or congruent. So I need to solve for this x, this long diagonal part of my bigger equilateral triangle, and I have to use the information that this right here is root 3 minus 1. I have a special right triangle right here. This one is a 30, 60, 90 triangle. These triangles have a special property where their side lengths, or the ratio of the side lengths, are like fairly easy to remember. If this is a 1, you can double it to get the hypotenuse, and then you can multiply it by root 3 to get the other leg. And I'll use this idea of this 1, 2, and a root 3 to help me with the actual triangle in my diagram. This side right here is part of this square. That's this one right here. That is root 3 minus 1. And it looks like to go from this leg back to here, I must divide by root 3. I'll take root 3 minus 1 and divide by root 3. That's this length right here. Now, I guess I could simplify it a little bit. I feel like it. I'll distribute the denominator. This right here is just a big number 1. And on the right side, I will rationalize my denominator just because I feel like that's the right thing to do. So that will be a root 3 over 3. And to get the hypotenuse, all I need to do is double it. That's that relationship that I'm seeing over here. So I will get 2 minus 2 root 3 over 3. Now, unfortunately, I'm not done. I didn't solve for x. I solved for the hypotenuse of this triangle. And it looks like x is actually equal to the hypotenuse, which I solved for, plus this little extra bit right here. Now, I don't really know what that length is just yet, so I want to call it just a variable for now, plus a. This a is going to be my little bit right here. And this is useful because I can find a similar relationship going on here. I know that this whole length is another x, and I could say that x is equal to this small bit right here, which was the 1 minus root 3 over 3 from my triangle. And if I add all of this stuff and take away a little bit, I will get the full side of the triangle right here, which is x. So I took the first little bit here, then I will add on a little bit too much, that root 3 minus 1. And then finally, I'll take away a small bit, and that should be the same length as the other part of my equilateral triangle, which is still just x. So now my geometry problem is an algebra problem. I have a system of equations with 2 equations and 2 unknowns. That means I can solve for both of them. I'll choose to use elimination here because I don't really care what this a value is. I would just rather eliminate or get rid of it and solve for x, because that's what the problem wants. On the left side, I have x plus x. That's just a 2x. And on the right side, I have a lot of terms. So I'm going to cross stuff off and be careful as I go. So I have a 2 plus a 1 minus 1. Okay, that's just 2. Then I have a plus a and a minus a. And this is the whole point of elimination, that I get rid of this one. And a minus a is just nothing, so I don't have to write anything down here. And then lastly, I got to deal with these root 3's. Okay, I got a minus 2 root 3 over 3. And I'm writing it like this just because I noticed something. So I have a 2/3 root 3. And I'm going to call this one a minus 1/3 root 3. And then this one right here is a plus root 3. If I'm taking away 2/3 and 1/3 of a root 3, then altogether that's just a minus root 3. And that one cancels out with the plus root 3. So all of those root 3 terms are just a 0. They don't do anything. And now I have a fairly easy equation, 2x equals 2. I know that x is 1. And I'm done. Now, as a little epilogue, let's go back to that other idea where these triangles might be different sizes. And so looking at my equations, this a value was that tiny little distance right there. And in one of my ideas, that a value could be essentially 0, or like as close to 0 as possible. And if we flip it around and think about it differently, we could also say that that a value is as big as possible. But if I do that, I just get the same picture, but rotated. So I think my answers for the other idea are already hiding on the page. What if I just call a 0 for both of these equations, and then I will get some kind of minimum value or some kind of maximum value for x. So let's try it. Looking at the first equation, if a is 0, well, I just get my answer. Maybe x could be 2 minus 2 root 3 over 3. Now, I guess it can't be equal to it because I do need the teeniest, tiniest little triangle down there. So I know that x is greater than this value, but it could be right up next to it. It just can't be equal. And then alternatively, if I set this equal to 0, I think I'm going to get an upper bound for this. I gotta be a little bit careful with like simplifying my terms, but I see that the 1's cancel out, and then x might be comparable to 2 root 3 over 3. And I believe this one is my upper bound, so x can't actually be this big. So I want to say x is less than that value. And what do you know? 1 is actually right in the middle of those two values, which makes sense because the 1 comes from the balanced diagram where everything is congruent and it's symmetrical. And so this ultimately is my solution set. Thanks for watching, and I'll see you in the next problem.